Hello, scholars. Let's go over continuity. I'll give you a few seconds to read the do now. Okay, so the goal here is to make this function continuous, meaning it's smooth on the curve. There's no breaks, no jumps, no holes, no vertical asymptotes. Okay, so if you look at this first function they gave you, you'll see that you can cancel the common factor, x minus 2. Now, if you remember, when you cancel a common factor, that means there's a hole at x minus 2 equals 0, meaning there's a hole at x equals 2. Okay, and the leftover graph is y equals 2x plus 1. So if you just sketch that, that means that at 2, there's a problem. There's a hole there. So if I had a 2x plus 1, meaning I had a line, at 2, there's an empty hole. Now if you look at this graph, this is not a continuous graph because I have a hole. Okay, so and then it says, what value of k will force this graph to be continuous? So what y value up here do we need so we can fill in this hole? We have to force a way to make this graph continuous. Well, let's see. I have 2x plus 1. Now, if I plug in 2 here, 2 times 2 plus 1, I plugged in 2 because x equals 2. That's the problem, right? This is the problem. So if I plug into 2 times 2 plus 1, that's going to give me 5. That means my y value should be 5 so that I can just fill in this hole. Now, if I fill in that hole, do I have any more problems? No. Now, I've made the graph continuous. So k here has to be 5. Okay, that's the only way this graph will be continuous. Okay, so I wrote a few reminders on continuity here. For a function to be continuous, there has to be a y value, meaning let's say we're focusing on this little graph here. Let's say I'm focusing on this point. There has to be a y value there. It can't be an empty dot, okay? So there should be no holes, like no holes, no jumps. Okay, it has to be a full-on y value, solid dot. Okay, the second requirement is the limit from the left must be equal to the limit on the right, all right? This is what it means. If I'm coming from the left side, it should end up at this dot. Let's say this dot is 2 or 3, okay? I'm just approximating. That y value should be the same as my limit from the right. If I follow this graph, it should end at 2 as well. So let me write that down mathematically. It means limit as x approaches a number, let's say c, from the left, has to be the same as the limit as x approaches the same number from the right. Okay, so these are just notations so we can remember what the notations look like. Very last requirement is the y value, so that means a solid dot, and the limits have to be all equal to each other. Okay, so the limit as x approaches c from the left has to be equal to the limit as x approaches c from the right. And it also has to be equal to the exact y value, so f of c. This guy is the exact y value. Okay? Alright, so that's how we can force or decide whether a function is continuous. Sometimes, though, we don't have continuous functions. That's just how it is. There are 3 main types of discontinuities that you'll see. The first type is right here in this pretty green graph. This one is called a vertical asymptote. The next one is this pretty orange graph right here. The situation here is that there's an empty hole at this x value, right? This empty hole. And so we call this discontinuity a hole. Another word for it is removable discontinuity. It's removable because, like the do now, right, we can force a y value to make the function continuous, like we did in the do now. The last example is this pretty purple graph here. This is a jump because as you look, if you follow the graph on the left side, suddenly you have to jump up to the next y value. That's why it's called a jump. Okay, there's also this thing called when you need to solve algebraically for wholes, vertical asymptotes, and zeros, okay? First thing, you have to factor the numerator and denominator. So I'm going to make up an example over here. Let's say I factor the numerator, x plus 1, x minus 3, and I also factor a denominator. Let's say it becomes 5, x minus 3, x plus 2. A quick reminder that when I see a common factor in the numerator and denominator, so if I cancel x minus 3 here, that is called a whole. So I'm going to write that down on the side, whole. X minus 3 equals 0, just like we did in the do now. So that's going to be x equals to 3. This is my whole. Now if I have a factor left in the denominator, I can set that equal to 0 and solve for it. And this is my vertical asymptote. Okay, so that means if I had a rough sketch here at -2, I'm going to have a vertical asymptote at -2, and I'm going to unfortunately have a hole at 3 somewhere, okay, like an empty dot. Lastly, this is just another extra thing. I know we haven't discussed zeros a lot, but this is from algebra. All you got to do, take the leftover numerator, set it equal to 0, solve it. This is your 0 right here. Meaning it crosses the x-axis at -1. So there's a dot right here at -1. Okay, so I don't know exactly what this graph looks like, but I do know that these points that I have, these discontinuities and the 0, are properties of the graph. Alright, so that's for the first page. Tune in to the next video for the next page.